Hi, it's Mark. Welcome to the Emergent Nature channel. Today I thought we would follow up to the You Can Solve Nature episode 1 video. And what I thought we would do today is just learn some basic concepts that help when thinking about the architecture of nature. So far I think there's 3 things I want to talk to you about. One is the absolute observer. Another one is zooming across scales with the absolute observer. And a third, maybe we'll get into a little bit about how point charges work. So the recap of the first episode is that about 125 years ago, around 1900, scientists missed a fantastic opportunity to discover the architecture of nature. So what we want to do is come up with a new ontology that uses point charges. We want to discover the architecture of nature. And if you're game, you can discover it as well on this series. I'll keep the hints to a minimum for a while so you can try to figure things out. Last time we said there was 3 things we need to change to the architecture that was considered around 1900 for point charges and was falsified. One thing was the magnitude of the charge on the geometric point charges. The idea at the time was that a point charge would be the magnitude of an electron or a proton. So the minus point charge would be the electron, the plus point charge would be the proton. They also said that the maximum speed limit of a point charge, if it's moving, is equal to the speed of a photon, which we call c, the speed of light. And the third thing they said was that the electric potential field emission from point charges also traveled at c, the speed of light. So those 3 things we've got to change in our architecture. One thing we have in common with the point charge architecture from 1900 is that we're working in a Euclidean void of time and 3D space, just like they were. The Euclidean voids are really simple. It's just a box with no walls, no sides, no tops, no bottom. And the whole universe would be just a huge 3D space, nothing in that at all, not a single thing. No, I mean, it's well beyond what we would call a vacuum. There would be nothing. There would be no space-time that's stretchy and curvy, like Einstein said. There would be not a single particle. There'd be no markers to identify where you are, where the virtual absolute observer is, and no scales. You couldn't tell anything from this absolute space. The other thing we have in common with the classical world is the concept of absolute linear time that only moves forward. So it's not stretchy, not curvy. Those are the things we need to keep as the baseline. Now, let's talk about the absolute observer. So the absolute observer doesn't use photons. Actually, it turns out one of the difficulties with modern general relativity and quantum mechanics is that they're using photons for almost all measurements. This observer doesn't really exist. It's virtual, so it's just something you can think about. But you can place the virtual absolute observer anywhere in 3D Euclidean space and at any scale in 3D Euclidean space. You can also have this absolute observer look at the tiniest time scales or the largest time scales. After we talk about the absolute observer for a while, we're going to get into zooming. And zooming is how you move between these scales in your mind. We'll get into some zooming techniques that'll make you comfortable with it and you can just move back and forth, just like you go up and down an elevator. We have our virtual observer who lives in absolute space and absolute time. And we can put this observer anywhere in the middle of any interaction of point charges. And we can watch it from all angles in our mind. We can slow it down. We can speed it up. You could have, let's say you have an assembly that could span many orders of magnitude in scale or frequency. So you could have one part of the assembly that's something really tiny. Let's just say 10 to the minus 34th as an example. I don't know if that's possible. You could have another part of the assembly where point charges are operating at, say, 10 to the minus 29 meters. These are just examples. You could have another third part of the assembly operating at 10 to the minus 26 meters, for example. The virtual observer can move around absolute 3D space and linear time as the virtual observer sees fit. And they're not using photons. They're really just based on reality, or your vision of simulated reality. So you can have to develop some intuition about how point charge systems work. That's not hard. We will take each part on its own so you learn how each part works. How would you consider zooming, right? So like, obviously if I stand here and move the camera away from me, it's looking like I'm zooming out. If I pull the camera in towards me, it looks like I'm zooming in, right? So that's one form of zooming, but we're not zooming very far there. Imagine you're zooming out by a factor of 100 or 1,000, right? If you took this camera and moved it 100 yards away from me instead of the length of my arm, which is about 1 yard, I would look pretty small. And if you moved it 1,000 yards, I would look even smaller. Those are all orders of magnitude. Multiplying by 10, dividing by 10, that's what I mean when we talk about an order of magnitude. So we want to be able to go from 10 to the minus 44 seconds, or 1 over 10 to the 44th seconds. That's a very short period of time. Obviously we can't even come close to measuring that today in our experiments, our laboratories. And we won't be able to go to this time in the present, where 1 second equals 1 second. And then we want to be able to, just like we measure days, months, years, decades, centuries, we want to be able to zoom out to even longer time spans, right? Scientists currently say the age of the universe is about 13.8 billion years. So that's a long time, right? So we've got our absolute observer. What does it mean that they don't use photons? Well, photons are tricky things because we're going to show that photons are actually an assembly of point charges. Think about what that means. You're using an assembly of point charges as your main observation vehicle, but photons are moving through space-time, which is made of point charges. And there's interaction. And space-time being made out of point charges is going to explain how Einstein gets his curvy, stretchy space and time. In essence, this means that photons are not a great medium with which to think about the universe, at least not without transforms, at least not without understanding all the things that affect a photon's speed and its energy loss. We have to understand all that in order to really use photons to get an accurate view. If we understood everything that affects a photon and everything that affects the space-time assemblies, then we could make a model showing what the absolute observer sees. And by sees for the absolute observer, I mean knows, right? They know because it's possible to do simulations to figure out what's going on. However, since point charges are smaller than photons, there's what makes photons. We don't have a way to observe with individual point charges themselves. I mean, science doesn't even know they exist yet. right? They think they falsified it 125 years ago. So this is a great thing about this absolute observer. They just don't have to worry about all the things that you have to worry about when you're dealing with Einstein space and time. Now, like I said, once we build up the space-time assemblies and the photon assemblies and the fermion assemblies, then you'll see how Einstein's space and time works and why we see these effects like curvature of space-time and dilation of time. We'll see how that all works, and it will make total sense. You'll even see why the scientists currently think that the speed of a photon is constant. It's not. It actually depends on the space-time assemblies that photon is traveling through. We're going to be talking about a very low fundamental level, where there's a minimal set of ingredients. There's going to be our Euclidean space and time, and there's going to be two kinds of point charges. A positive point charge, which we call the positrino, and a negative point charge, which we call the electrino. And there's going to be some enormous density of those per unit volume in the universe. And they're also going to be carrying an energy density in kinetic and potential form. So last time, your objective was to figure out the magnitude of the point charge. We know it's not 1, where 1 is the value of the electron or the proton. So you got to figure something out. You've got to match up to quarks at minus 2/3, minus 1/3, plus 1/3, plus 2/3. And you have to be able to hit the neutron. You figure out a charge that you can put groups of point charges together. We'll figure out later their motion, but just figure out the groups that would give you all the possible particle charge values. That was your challenge from last time. So let's talk about zooming some more. So one way to think about zooming is like you're in an elevator. Let's say the elevator on ground floor is 10 to the 0, so that's 1. But your elevator only operates in orders of magnitude. So the next stop on the elevator upwards is 10. The second stop is 100. The third stop is 1,000. So now if we go in the elevator on the ground floor and we want to go smaller, our elevator will push the down 1 button. It says -1. And that means we're going to 10 to the -1 meters. If we go to floor -2, that's going to mean 10 to the -2, which is 1 over 100. So the doors open, you get out, you're going to be looking at things that are that size, 1/100th the size of where you went in. So you're going to be pretty small. So that's another way to think about zooming. Imagine you're in an elevator and it's going to take you to higher scales or lower scales. You just get off where you want to go. And that's mentally what you have to do, because sometimes it can be kind of strange to think about continually zooming in, just straight to your target. That takes a while to practice to get there. But I did say targets. That's another good point. When you're going to try zooming, you really need to have a target in mind, because you're going to zoom to that target. So let's say you want to zoom into a proton in a water molecule. So water is what? H2O. So 2 hydrogens. So that's going to be 2 protons there, plus 2 electrons. And it's going to be an oxygen, however many protons there are in an oxygen. So if you want to zoom into one of those, first you got this big bucket of water, and you want to zoom into 1 proton. You're going to just kind of imagine zooming into 1 proton. There's many protons in that bucket of water. But first you zoom in, you get close to the water, you dive into the water. Now you start, taking your elevator down to smaller and smaller scales. Eventually you're going to get to the point where you say, oh, I'm coming up on a water molecule, and you're going to see the protons and neutrons of the H2O kind of moving around. Well, actually, first you'll see the electrons from far away. And that's probably all you'll see, because they're flying around the nucleus. And the nucleus is where the protons and neutrons are. But now you're so zoomed in, these things look like planets in a solar system, because you've rescaled. You might be down at 10 to the minus 10th, you take your elevator down to minus 15, now you're at 10 to the minus 15th, but you get out, everything the virtual observer sees in absolute space is going to look really far away, right? Once you get down to the nucleus, the protons and neutrons, the electrons are like moons to you, or even farther away. I know, you'd have to do all the math, but I'm trying to just give you the concept. So kind of also think about zooming to smaller scales as zooming in on things like solar systems, right? So now you zoom down to the proton and you see the proton. What does science say is inside of a proton? Let's see, it's 3 quarks, and it would be an up quark, a down quark, and another up quark. So now you're just looking at one proton. You're going to zoom in farther, and you can look around and you say, oh, there's 3 quarks, and oh, look at how they're interacting. Oh, that interaction, that's what a gluon does. Then you start saying, well, what are these quarks made of? And that's when you're getting down close to the base of nature, because the quarks follow an architecture. All the fermions follow an architecture. All the bosons follow an architecture. Space-time follows a point charge architecture. You're going to look at these fermions and you're going to know now, because we're trying to find the architecture of nature, you're going to assume that it's there based on the fact that we found a pretty gaping hole in science from 125 years ago. You're going to assume they just missed the architecture. So now you're down to the quarks, and you want to look inside the quarks and figure out, how do point charges arrange themselves to make a quark? And guess what? I'm going to give you a clue. It's also like a solar system. And you're going to find, I think they're on the outside, a bunch of personality charges that give the fermions their charge. And then you'll find a nucleus. And then you'll find another nucleus. And then you'll find a third nucleus. And these are all formed by point charges. So those are some more clues if you're still looking for the magnitude of the point charges used in nature. I'm starting to give you some hints about the architecture. And we can zoom in. We're looking at a quark, we go, oh, that's a quark. Normal science just stops there and says, we don't know, we gotta do a lot more experiments. We gotta spend, billions of dollars on experiments and people trying to figure that out. But we don't, really. We should have known the architecture of nature 125 years ago. It's so easy. But current science says the quark is an indivisible unit, even though they know there's more to the story. They just don't understand how. Now, when we drill in, let's say we go in our elevator again, we take it down 3 more floors, we're 1,000 times closer to the quark. That's our target. And we look and we say, hey, let's use our zooming on time to slow this thing down, because now it's such a small size looking at this quark, and its parts are moving so fast that our absolute virtual observer can't tell what's going on. So slow it down. You slow it down in your mind until you can see how these point charges are moving. But each level of the architecture is moving at a different speed. So we're going to first see these personality charges in most of the fermions, and we're talking about a fermion, that's the quarks. And so we're going to blow past the personality charges. We're going to go even smaller. Get into our elevator, go down a few more floors. Now we're 1,000, 10,000 times closer to the center of the quark, and maybe we'll start to see the first part of the nucleus. And the first part of the nucleus is just going to be a positive and a negative point charge orbiting each other. Kind of like in a circle, but they're precessing, and there's all kinds of other things. So it just might kind of look like they're moving around the surface of a sphere, or an oblate spheroid, which is like if you took a totally round balloon and you squeezed it, that would be an oblate spheroid. It's kind of a squished sphere. So now we go, oh, are we done? You know, is there anything below this? Well, let's get back in our elevator. Gonna go down several more floors. We're gonna get out of our elevator, and now we're another 1,000, 10,000 times closer to the absolute center of the quark. And we look back and we see, because we've zoomed, we see that first part of the nucleus, the electrino and the positrino, you know, kind of on opposite sides of us, rotating in some orbit around us. And they're really far away, so they just look like pinpricks to us because we've come down 3 more floors in our zooming elevator. Okay, now we're at the second layer of the quark nucleus, and we've slowed time down. We're way far down in our space elevator, so we're looking at an incredibly tiny scale. And what do we find? We find another electrino-positrino pair rotating, orbiting on the surface of a sphere or an oblate spheroid. But we can slow it down, and then they're just moving slowly, and we're kind of watching them, and we look back up at the first layer of the nucleus. It's looking like it's not moving at all. So now we know the second layer. Is there anything farther in towards the center of this quark? Why now? Well, we get back in our space elevator and we zoom. We zoom down a few more levels to get logarithmically closer to the center. Every floor we go down, it's 10 times closer to the center. And you just have to let yourself free with that idea. Don't worry about it. Just say, that's how it works. And we're just going to get closer and closer. And that's how you imagine getting towards the center of a particle assembly. And so the doors open, we hop out, and we go, is there anything else in the center of this quark? We've already found 2 levels of binary orbitals. What are we going to find here? And you get out, and there's a 3rd level of binary orbital. And that's it. Why 3? I think it's because we have 3-dimensional space. And so if you think of 3 orbitals, even though they're at very different scales, you could have one orbital moving like in the XY plane, and one orbital moving, you know, in another plane, and then there's a 3rd plane. Which way did I do? So then there's a 3rd plane going this way, right? So just like if you took the corner of a box, right? One side is a plane, the other side is a plane, and the top is a plane. So you could imagine those 3 planes, the orbitals will be there. They're at very different scales, so they're not going to collide with each other, right? But why 3 still? Why? Well, we have 3-dimensional space, so still, why 3 orbitals? Well, because probably if you had 4, they don't have like as much independence, and they could presumably go unstable or collide with each other. I think it's just a natural thing. Because we have 3-dimensional space, these assemblies are going to find that 3 encapsulated binaries, point charge binaries, is what works, and that's how particles are made, and that's what survives. Anything else that forms probably is unstable and flies apart, or is easy target for a collision with something else and flies apart. So you kind of get this survival of the fittest thing from Darwin, except it's not quite like that. I mean, there's some more characteristics. One is going to be almost like cloaking. Like, what was it? Who was it did the cloaking? The Romulans in Star Trek? Remember, each of these binaries in the nucleus of the quark and of every standard model particle, it's a positrino and an electrino orbiting around each other, because those point charges are equal and opposite. So that's one thing already. Is like, if you're flying by that thing as a bigger particle assembly and you're flying by, you might not even know it's there from a charge point of view. Now, on the other hand, moving charges create fields, and those fields are going to have a lot to do with how nature works. So one binary orbiting around is not necessarily stable, because its fields are going to be quite apparent to something going by, especially at the poles of the orbit. So the poles would be, if the orbit is going this way, then the axis of orbit goes this way, and that's where the poles are, right? So the poles are on the axis of the binary orbit. So then let's say, got a really high energy environment, and you get one of these point charge binaries, really tiny, it's way down near the bottom of the elevator, minus 35 or something. And let's say you're in an environment where there's other point charge binaries, but some have had collisions or broke apart and then formed new ones. There's a lot of energy transfer happening. And so let's say there's another binary, but it doesn't have quite as much energy. Well, it turns out the way the physics works, if it has less energy, it's going to have a larger radius of orbit. And so somehow we have this larger binary, which is still quite small, meet our super tiny binary. And for some reason, they want to couple together. They want to the smaller one wants to get in the center of the bigger one, is the way I figure it. That's my hypothesis. But let's say that happens, and it makes kind of this sub-assembly now of two binary assemblies joined, coupled into one double binary assembly. But space is 3D, so this is still not a totally stable environment, because the fields that it casts off, the potential fields it casts off, will interact with other particles. So let's say this whole thing happens a third time. Now, our double binary system meets a third binary at even lower energy. They all combine, and you have this triple binary at very different magnitudes, very different energies. Now, the part where I was talking about stealth or cloaking is that electric potential has this effect called superposition. So if you're giving off potential, that potential wave can be canceled by the opposite potential waves from somebody else. So wherever those two things meet, there can be a cancellation. So my theory is that this triple binary finds an orbit, a combined orbital. It evens out some energy between all three if it adapts to a combined orbital that has an extremely low footprint in potential around it. So it's almost invisible from the point of view of the absolute observer and the point of view of potential fields. So it would only be visible at the poles of each orbital axis. So you have three orbital axes, right? Because you got one going this way, one going this way, one going this way. And that's three orbital axes. And then on either end, there's a north and a south pole. So you have three orbital axes. Each orbital axis has two poles. So 3 times 2 is 6. You've got 6 locations around this triple nucleus thing that you could put a personality charge. Maybe at, again, a much higher floor on the elevator. It's a much larger radius than this triple nucleus, but an electrino or a positrino could get stuck in each one of the poles, each one of those 6 poles. That's kind of a really cool architecture, and that's how I think fermions work at the most basic level. Now, the idea of our zooming space elevator is really just a mental crutch. You don't need to use that. Once you do that for a while, you'll get the idea that you're just zooming into a target. So you just kind of like, one of those Star Trek things when they go to warp speed and all the stars just go, right? They blur like that. You can think of it that way too, right? You don't really have to worry until you start getting down close to your target, and then you can kind of say, okay, I'm getting close to this point charge assembly, and now I can see it. It's going to look like a little solar system, except following a different architecture where the point charges are operating with that. So if you want, the space elevator is a good way to think about it to begin with, but eventually you won't need that. And same thing with time. I mean, you can easily imagine, we just think about we have slow motion all the time in videos, sports replays, anything. We know how to slow things down. And it's just a matter of doing that, slowing it down to incredibly slow speeds or speeding up to incredibly fast speeds. And as I said before, once you've zoomed in, don't forget to kind of turn around and you have your virtual observer look at the different parts of the assembly from the inside, right? So you're going to be looking at the second binary, and you can have, one way up here, and then, if you then turn the other way and look, you're going to see one opposite there, and they will rotate around the center where you are at the innermost binary. And if you look a little farther out, logarithmically, which may mean 1,000 or 10,000 times as far as the second binary, you'll see the third binary. And then if you look even farther than that, you're going to see 6 satellites way out there, and those are your personality point charges that help determine what type of particle you are. What's that? How can we map that to quantum theory? Well, we're going to have to figure that out. Mapping is the key. Quantum theory is essentially right. It's just at a wrong level of ontology. So everything we do, we're going to have to map and reproduce what's in quantum theory and what's in general relativity. Except the narratives. Their narratives are pretty messed up. But that's okay. I mean, that's what happens in science. It's not okay that it took 125 years to figure it out, but it is okay to get things confused and then go back and fix it. And I'll do an episode sometime with my critique of the scientific method for not having a proactive way to tell when fields are in crisis and that a wrong turn might have been taken or a missed opportunity might have happened. Figure out, a lot of this we could just figure out with logic and problem solving because we already know where it has to map, right? We already know that general relativity and quantum mechanics work and are accurate. I'm going to introduce one other term because I will probably just use it, so I better introduce it before we go on, which is that I call our triple binary nucleus, I call that the Noether core, or Noether core. There was a scientist by the name of Emmy Noether, sometime early 1900s, I think, and Emmy did a tremendous amount of work on the principles of conservation and momentum, and it turns out, I think this triple binary maps directly to a lot of her work. So my suggestion is that we call this triple binary nucleus the Noether core, and after Emmy. So we have the Noether core surrounded by personality charges, and that's how we're going to build all the fermions. We're going to find a lot more just in this architecture. We'll find dark matter, we'll find dark energy, we'll figure out how inflation works, how expansion works. It's all in this architecture, including Einstein's stretchy, curvy space-time.